For 3 decades, the most advanced engineering minds on the planet agreed on one singular, unshakable truth. They said that if you wanted to build the future, you had to go through a single small town in the Netherlands. They said that the machine required to power the next century of human progress. The EUV lithography machine was so complex, so physically demanding, and so impossibly precise that no other nation could ever hope to replicate it. This wasn't just an opinion. It was a multi-billion-dollar geopolitical fact. The CEO of ASML famously laughed at the idea of a competitor, suggesting that even with the blueprints, a rival would be decades behind. Washington believed this so deeply that they turned this Dutch monopoly into a technological chokepoint, a silicon wall designed to freeze the progress of their greatest rival in time. They told the world it was impossible for China to bridge this gap. But in early 2026, a single report from Reuters sent a seismic shockwave through the halls of the Pentagon and the boardrooms of Silicon Valley. The impossible had just happened. In an unmarked high-security facility in Shenzhen, the silicon curtain has been torn open. China hasn't just built an EUV machine. They have triggered a technological insurgency that changes the rules of global power forever. To understand the scale of this masterstroke, you have to understand the sheer absurdity of the machine we are talking about. Imagine trying to throw a stone and hitting a specific atom on the moon. That is the level of precision we are dealing with. This machine, the EUV lithography system, is the only reason your smartphone isn't the size of a brick. It is the only way humanity can etch circuits so small that a human hair looks like a 6-lane highway by comparison. We are talking about features measured in nanometers, billionths of a meter. At this scale, the laws of physics start to break down. Standard light is too fat to draw these circuits. It's like trying to write a novel using a massive paint roller. You need extreme ultraviolet light. But there's a problem. EUV light doesn't exist naturally on Earth in a way we can use. It is absorbed by almost everything, including the very air we breathe. The process to create this light sounds less like manufacturing and more like a high-energy physics experiment. You take a droplet of molten tin, just 30 microns wide, and you drop it through a vacuum. As it falls, you hit it with a high-power CO2 laser. But you don't just hit it once. You hit it with a pre-pulse to flatten it into a pancake shape, and then a microsecond later, you hit it again with a main pulse of 30 kilowatts. This vaporizes the tin into a plasma reaching temperatures hotter than the surface of the sun. This plasma emits the golden ticket, light with a wavelength of exactly 13.5 nanometers. This is what the world's entire digital economy relies on, and for 30 years, only one company, ASML, could make this work. They spent $6 billion and 3 decades of failure to master this tin drop dance. This machine is the size of a double-decker bus. It weighs 180 tons. It requires 40 freight containers and 3 747 cargo planes just to ship a single unit. It costs $150 million, and that's the cheap version. Because ASML was the only source, they held a total monopoly. If you were Intel, TSMC, or Samsung, you didn't just buy a machine, you begged for a spot on a years-long waiting list. But for China, the list didn't even exist. In 2018, under heavy pressure from Washington, the Dutch government pulled the plug. They revoked the export licenses. China was barred from the future. The strategy was simple. If China couldn't buy the machines, they couldn't make the chips. If they couldn't make the chips, they couldn't lead in artificial intelligence, autonomous weapons, or quantum computing. The West believed they had built a wall that no amount of money could climb. But while the world was distracted by trade wars and public posturing, Something was happening in the Nanshan district of Shenzhen. This wasn't a massive, sprawling government campus with thousands of employees and propaganda banners. It was a technological insurgency. In an unmarked building, a core strike team of 170 leads, backed by a state-mobilized supply chain of 10,000 engineers, were beginning a project that the rest of the world considered impossible. They weren't just trying to build a machine, they were trying to build a nation's survival. They called it a Manhattan Project for the digital age, but unlike the original, this one had to be built in total shadow, under the constant gaze of global intelligence agencies. The Western consensus was that China was at least 15 years behind. Even the most optimistic analysts said 2035 was the earliest China could even dream of a prototype. They pointed to the optics gap. You see, the mirrors inside an EUV machine are the smoothest objects ever created by human beings. If you scaled one of these mirrors up to the size of the United States, the largest bump on its surface would be less than a millimeter tall. These mirrors were a German secret, guarded more closely than nuclear codes. Without these optics, an EUV machine is just a very expensive pile of scrap metal. The Americans were confident. They had the Dutch hardware, the German optics, and the American light source patents. They held all the cards, or so they thought. What they underestimated was the human intelligence factor. In 2019, a quiet exodus began. High-level engineers, many of them ethnic Chinese who had spent decades in senior roles at ASML and Zeiss, started disappearing from the European tech hubs. They weren't just leaving for better pay, though reports of $700,000 signing bonuses and private villas in Shenzhen were common. They were moving because they saw the silicon curtain falling, and they wanted to be on the side that was building the ladder. These weren't just workers. They were the institutional memory of the EUV industry. They knew where the dead ends were. They knew which experiments had failed in the 90s and why. They were the ultimate shortcut. The Shenzhen team made a radical choice. They realized that if they tried to copy ASML's 30-year-old path, they would always be 30 years behind. To win, they had to leapfrog. They had to find a different way to generate that 13.5 nanometer light. While the West focused on perfecting the molten tin method, the Chinese team began experimenting with alternative solid-state lasers and specialized particle accelerators. They weren't looking for the most elegant solution. They were looking for the one that worked with the materials they could source domestically. This was the birth of the subterfuge strategy. By the time US intelligence realized the Shenzhen lab wasn't just a research center, the first prototype was already being calibrated. For months, the project was fueled by a singular, obsessive energy. But money and motivation can only get you so far when you are fighting against the laws of physics. The team in Shenzhen quickly realized that the Western sanctions weren't just a hurdle, they were an evolutionary pressure. By cutting China off from the global supply chain, Washington had inadvertently forced the Chinese engineers to do something ASML never had to do. They had to reinvent the wheel while the world was watching. This is where the subterfuge strategy shifted into high gear. While the US focused on blocking shipments of physical machines, they struggled to block the flow of ideas. The Shenzhen team wasn't just composed of young graduates from Tsinghua University. It was anchored by what the industry calls the gray eminences. These were veteran engineers who had spent decades inside the clean rooms of Veldhoven and San Diego. They didn't need to steal blueprints. They were the blueprints. They brought with them the tribal knowledge of semiconductor manufacturing, the tiny, unwritten details about how a specific vacuum seal reacts to heat, or how a laser's frequency shifts after 6 hours of continuous operation. However, even with this elite brain trust, The hardware was only half the battle. The team faced a brutal reality. They couldn't buy the ultra-pure, specialized mirrors from Zeiss in Germany. In the world of EUV, the mirrors are everything. They are polished to an atomic level. If you can't get them, you can't focus the light. If you can't focus the light, you don't have a machine. Instead of giving up, the Shenzhen group turned to China's burgeoning space program. They recruited optics specialists who had spent their careers building deep space telescopes and high-powered military satellites. These scientists didn't know much about microchips, but they knew everything about the behavior of light in a vacuum. They began a grueling 2-year process of perfecting ion beam figuring, a method of using a stream of ions to shave off individual atoms from a mirror's surface until it reached the impossible smoothness required for EUV. But as 2023 rolled around, the project hit a wall that nearly shattered the entire operation. The team had assembled the mirrors. They had built a domestic laser source. They had engineered a vacuum chamber that was arguably more advanced than the ones used in Europe. On a humid night in October, they prepared for the first full-power test. The atmosphere in the lab was electric. Billions of dollars and the pride of a nation were riding on this single moment. They powered up the system. The laser fired. The tin droplets began their 50,000 per second descent. The result was a disaster. The sensors showed that less than 5% of the light was actually reaching the silicon wafer. In the world of commercial manufacturing, 5% is a death sentence. It meant the machine was essentially a very expensive, very high-tech flashlight. For 3 weeks, the lab became a ghost ship. Engineers worked 20-hour shifts, sleeping on the floor and eating instant noodles, desperately trying to find the leak in the system. Every component tested perfectly in isolation. The laser was powerful enough. The mirrors were smooth enough. The vacuum was tight. But when they worked together, the system was blind. They eventually discovered that the problem wasn't the hardware at all. It was the timing. The window to hit that falling tin droplet is 30 billionths of a second. If the laser is off by even 1 nanosecond, the plasma doesn't form correctly, and the light is scattered. ISML had solved this with a proprietary software suite they had spent a decade perfecting. Software that was locked behind layers of encryption China couldn't crack. The Shenzhen team was staring at a decade of software development that they needed to finish in a month. This was the moment of the great pivot. They realized that human programmers couldn't solve this fast enough. So engineers used AI to simulate the vacuum environment to predict tin drop behavior in real time. They built a specialized neural network and fed it every single data point from the failed tests. Every vibration, every temperature shift, every micro flicker of the laser. They let the AI play with the machine in a virtual simulation, millions of times an hour, searching for the perfect timing sequence that human logic couldn't see. It worked. The AI discovered that the timing didn't need to be perfect. It needed to be adaptive. It needed to change every millisecond based on the heat of the chamber. On February 9, 2024, the machine was powered on for its second major test. The output didn't just hit the target, it surged to 70% efficiency, nearly matching the commercial standards of the West. The impossible machine was alive. But this success created a new, even more dangerous problem. In the world of geopolitics, a breakthrough this big is a target. If Beijing announced it, they risked an even more aggressive response from the West. If they kept it secret, they couldn't scale it. They chose the shadow. For 8 months, the machine ran in total silence, producing test batches of advanced chips that technically shouldn't have existed. The secret didn't break because of a spy or a disgruntled employee. Analysts at Tech Insights found 7-nanometer chips in the Huawei Mate 80 Pro that showed signatures of EUV exposure. signatures that weren't supposed to be there. Supply chain analysts in Taiwan and the US started noticing a ghost in the data. China's domestic chip production numbers were climbing at a rate that defied the laws of physics, unless they had a new tool. The chips being found in new Chinese smartphones weren't the old, clunky 14-nanometer versions the embargo was supposed to lock them into. They were 7-nanometer and 5-nanometer masterpieces. The silicon curtain hadn't just been breached, it had been bypassed entirely. When US intelligence finally confirmed the existence of the Shenzhen prototype in early 2026, it was a full-scale panic. They realized that the chokepoint strategy had failed. By trying to starve the Chinese tech industry, they had accidentally forced it to become self-sufficient. They had turned a customer into a competitor. And as the reports filtered in throughout early 2026, one detail stood out above all others. The Chinese AI-driven timing system was actually more efficient than the legacy software used by ASML. The reaction in Washington to the realization that their technology blockade had failed was not just one of policy adjustment. It was a frantic, high-stakes realization that the very foundations of American technological hegemony were shifting. By December 2024, the U.S. Commerce Department prepared what many called the nuclear option of trade restrictions. This wasn't just about banning machines anymore. This was a total effort to dehydrate the entire Chinese semiconductor ecosystem. They targeted the ink of the process, the specialized photoresist chemicals that react to EUV light. They targeted the ultra-pure tin required for the plasma generation. They even targeted the specialized software updates for secondary components that weren't even related to lithography. It was a seismic attempt to build an airtight cage. But the architects of this new sanctions net missed a critical detail about the Shenzhen team's methodology. From day one, the leadership in that unmarked building had operated under a doctrine of total domesticity. They had seen the 2018 embargo not as a temporary hurdle, but as a permanent state of war. Every single component of their prototype, from the smallest vacuum seal to the massive high-power CO2 lasers, was built with a dual-track system. If a part could be sourced from a friendly or neutral foreign entity, they used it for the initial tests to save time. But in the background, a shadow team was simultaneously tasked with building a 100% domestic version of that exact same part. When the December 2024 sanctions landed, the world expected the Shenzhen lab to grind to a halt. Instead, the facility didn't even flicker. The mirrors weren't from Zeiss. They were from a specialized optics plant in Changchun. The lasers weren't from American providers. They were an evolution of Chinese industrial laser technology used in high-end manufacturing. The silicon curtain that Washington tried to drop only ended up sealing China inside an ecosystem of its own making, an ecosystem that was now completely immune to outside pressure. This was the master stroke. By trying to weaponize the global supply chain, the West had inadvertently incentivized the creation of a rival chain that they had zero visibility into and zero control over. The technical data that began leaking out in early 2026 confirmed the nightmare scenario for Western chip makers. The Shenzhen machine had achieved a conversion efficiency of 3.42%. To the average person, that sounds like a small number. To a semiconductor physicist, it's an earthquake. For years, the industry standard for a commercially viable EUV machine was roughly 3%. Anything less, and you're spending more on electricity than the chips are worth. At 3.42%, China hadn't just built a science experiment, they had built a factory-ready weapon. They were now capable of mass-producing the 5-nanometer and 3-nanometer chips that are the lifeblood of modern warfare and artificial intelligence. This is where the story shifts from an engineering triumph to a geopolitical crisis. The monopoly held by ASML was never just about business. It was a security guarantee. As long as the West controlled the EUV chokepoint, they controlled the ceiling of Chinese military capability. Advanced chips are the brains of hypersonic missiles, the engines of autonomous drone swarms, and the backbone of the massive data centers required to train artificial general intelligence. If China could manufacture these chips domestically, the strategic offset that the United States had relied on for decades would vanish overnight. The lab in Shenzhen didn't stop at one machine. In a move that displayed an almost terrifying level of resource allocation, they transitioned from a research phase to a blitz-scaling phase. Intelligence reports suggested that by mid-2025, they were no longer just testing a prototype. They had constructed 12 different versions of the machine simultaneously. In the West, such a project would be bogged down by quarterly earnings reports, shareholder lawsuits, and the need for immediate ROI. But the Shenzhen team had a blank check and a singular mandate from the highest levels of government: move faster than the sanctions can evolve. They adopted a strategy of evolutionary competition. Each of the 12 machines featured slight variations in their AI timing algorithms, mirror coatings, and laser frequencies. It was a Darwinian approach to engineering. The machines that underperformed were stripped for parts. The ones that showed even a 1% improvement in yield were immediately moved into a pilot production line. This allowed them to compress 10 years of industrial refinement into less than 24 months. While the Dutch and the Americans were debating the ethics of further export bans, the Chinese were already etches circuits on their third generation of domestic wafers. The true gravity of the situation became clear when rumors began to circulate within the Dutch tech corridor. ASML, the crown jewel of European technology, was no longer just watching China as a lost market. They were watching them as a technical threat. Their own engineers began to analyze the leaked data regarding the Chinese AI adaptive timing system. For decades, ASML had used a fixed calibration model because it was reliable, and they had no reason to change what was already working. But the Chinese, born out of necessity and desperation, had built something more flexible, more resilient, and arguably more sophisticated. For the first time in 30 years, the teacher was looking at the students' homework and realizing they had been surpassed. The implications of this shift extend far beyond the balance sheets of semiconductor companies or the trade deficits of nations. We are witnessing the birth of a new era in human history, one where the fundamental fuel of civilization, compute, is no longer a centralized resource controlled by a Western alliance. For decades, the global power structure was built on the assumption that the most advanced silicon would always be a product of the democratic world. That assumption was the bedrock of every military strategy, every economic forecast, and every AI safety framework in existence. By breaking the EUV monopoly, the Shenzhen team didn't just build a machine, they dismantled a global hierarchy. The most immediate and terrifying consequence for the West is the sudden acceleration of China's artificial general intelligence programs. AI is a game of two things: data and compute. While China has never lacked for data, the US-led embargo was specifically designed to starve their AI models of the high-end processing power required to reach the next level of intelligence. It was a digital siege. But with a domestic EUV pipeline now operational, that siege has been lifted. The compute gap that was supposed to last until the late 2000s and 30s has evaporated. This means that the race toward AGI, a technology that will define the winner of the 21st century, is now a dead heat. The strategic cushion Washington thought it had has been replaced by a high-velocity scramble for dominance. In the military sphere, the shockwaves are even more profound. The modern battlefield is increasingly defined by autonomous systems, precision-guided munitions, and real-time electronic warfare. All of these depend on the very chips that the Shenzhen machine is now producing. By achieving self-sufficiency in EUV lithography, China has ensured that its military hardware will never be frozen by a foreign sanctions regime. They have achieved technological sovereignty in the most critical sector of the modern age. The era where a single policy change in Washington or a single export ban from the Netherlands could cripple a superpower's military evolution is officially over. The economic fallout is just as seismic. For 30 years, the Dutch-American partnership in high-end lithography was the ultimate insurance policy for the global tech industry. It provided stability, controlled the pace of innovation, and ensured that the most sensitive technology remained in a closed loop. Now, that loop is broken. We are moving toward a bifurcated tech world. Two separate silicon ecosystems, two separate supply chains, and two separate sets of standards. This isn't just a trade war. It is a fundamental splintering of the digital world. The efficiency of a globalized market is being traded for the security of regional fortresses. There is a deep, almost poetic irony in how this story unfolded. By attempting to use a monopoly as a weapon, the West inadvertently triggered the one thing that could actually destroy that monopoly: a desperate, well-funded, and highly focused competitor with nothing left to lose. If Washington had continued to sell the machines, China might have remained a dependent customer for another 20 years, content to buy rather than build. But by closing the door, the West forced China to build its own house. The Silicon Curtain didn't keep China out. It kept the West from seeing how fast China was moving inside. The experts were right about one thing. Building an EUV machine from scratch in under 4 years was impossible. It violated the established timelines of industrial development. It ignored the traditional paths of institutional learning. It defied the logic of the global supply chain. But what the experts failed to account for was the power of a technological insurgency. They failed to account for the convergence of a nation's entire scientific brain trust on a single existential problem. They underestimated what happens when some of the world's best engineers are given a blank check, an AI-driven mission, and the knowledge that their country's entire future depends on their success. As we stand here in 2026, the question is no longer whether China can build the hardware. That question has been answered with a resounding and undeniable yes. The new question is what happens to a world where the most powerful technology is no longer a secret shared by a few allies, but a contested frontier where the rules are being rewritten in real time. The era of the single-point chokepoint is dead. The impossible machine is now a reality, and with it, the global balance of power has shifted on its axis. We are no longer waiting for the future to arrive. We are watching it be etched, nanometer by nanometer, in the clean rooms of Shenzhen. The story of the EUV machine is a reminder that in the realm of high technology, there is no such thing as a permanent advantage. Pressure produces diamonds, and in this case, it produced the most sophisticated manufacturing tool in human history. The silicon wall has fallen, and what lies on the other side is a world that looks nothing like the one we knew just 5 years ago. The rules of the game have changed, the players have evolved, and the stakes have never been higher. If this breakdown of the global tech shift opened your eyes to the new reality of the Silicon Wars, make sure you hit that like button. The world is moving faster than most people realize, and we are committed to bringing you the stories from behind the curtain that define our future. Subscribe and turn on notifications so you're the first to know when the next seismic shift happens. and I want to hear your perspective on this. Did the West's attempt to gatekeep the future actually backfire and create a more dangerous, independent competitor? Or was this technological leap inevitable, regardless of the sanctions? Let's get the conversation started in the comments. This is a story that affects every single one of us, and the debate is only just beginning. Thank you for watching, and stay sharp. The future is being built right now. This is Signal Frontier. I'll see you in the next one.